So our main reference will be LeFloc, and then is the complex manifolds part of the course. And then for today and a little bit of tomorrow's lecture, half of tomorrow's lecture, not tomorrow, but next week's lecture, we're just going to be dealing with smooth manifolds. So for the smooth manifolds part of the course, there's another set of notes I've linked to on the website as well. Okay, so today it's just going to be all about smooth manifolds. That's going to carry on over week as well. So yeah, welcome to the course. And I've muted myself here, so if, just monitor the chat. I think if you want to ask a question, just ask it in the chat, and then we'll pick that up. Okay, so let's start. So let's start with what a definition of a smooth manifold is before we get to what a complex manifold is. Close the store. M-dimensional smooth atlas on a topological space M is an open cover of M together with local charts from each UI in the open cover to an open subset of Rm, I've indicated here, satisfying all intersections that are non-empty in the open cover, that the transition function, namely you do the inverse of the one chart map and then you use the other chart map, that's going to be a smooth map between open subsets of Rm. So let's be clear about this. Here is my topological space M. And here I've got two charts in the atlas, phi I and the phi j chart, and they're living on different open sets Ui and Uj. And what I want is the phi I gets me into some open set of Rm, and phi j is a homeomorphism from Uj into some open set in Rm. So on the intersection, I can consider this map here. And what I'd like, so that's going to be a map from this little section here to this little section of the open set here. And I want that map to be smooth. What does that mean? Now I've got a map between open sets in Rm. It's just a function of m variables. So it's got m components, and each component is a function of m variables. And each of those functions, you have infinitely many partial derivatives. So that's what a smooth atlas is on a topological space M. So we start off with the topological space M, and now we talk about a atlas on that. Just pause at any point and ask a question in the chat, and we'll, or just you guys who are here locally, stop me. So what does an atlas give us? An atlas on a topological space M allows us to say when a function is smooth. Obviously, I've got a topological space, so I can say when the function space is continuous. Now I'm allowed to say when it's smooth. Namely, we demand that for all charts in the atlas, that F composition phi I inverse is a smooth map from an open subset of Rm to R. See, here we've got a map F from M into R, M here. And I now have the ability to say whether this map F is smooth or not. Namely, for every chart Ui, phi I in the atlas, what I want is that this composite here, sorry, this map here, which is the composite of first doing phi I inverse and then doing F, I want that map to be a smooth map from Rm into R. And again, that just means that I've just got a function of m variables, and I want that to have infinite. So an atlas on M gives us a way to decide whether a given function is smooth or not. And we define two smooth atlases on M to be equivalent. They agree functions are smooth. Okay. And then we define an m-dimensional smooth manifold to be a Hausdorff second countable. These are just technical provisos, but it's a topological space M equipped with an equivalence class of an m-dimensional smooth atlas. That's the definition of a smooth manifold of M. Just if you, we'll never really care about these two concepts here, but just so that you know, Hausdorff means that a topological space is Hausdorff. Any two distinct points in it, find open set around each of those points which don't intersect each other. And second countable means that there's a countable basis for the good. Now we know what a smooth manifold is. Since we are category theory minded, or we think whenever you define a mathematical structure, you should talk about maps between such structures. So a map between smooth manifolds, so it has M and N. I'm not writing down the atlas on M and the atlas on N, but that's implicit. Yeah, I've sort of given it explicitly. A map between smooth manifolds is smooth if for all I and j, this composite map is going to be a smooth map from an open subset of Rm to an open subset of Rn. This is an m-dimensional manifold. This is an n-dimensional manifold. And I've got a map H from M to N, and I'm asking whether that's a smooth map. Remember, I know what a smooth function on a manifold is. Now I'm asking, when is a map between manifolds smooth? And the answer is, well, for every chart in M and for every chart in N, I can consider this composite, if non-empty. And I want this composite, which is a map from Rm to Rn, I want that to be a smooth map. And a smooth map from a manifold M to a manifold N is called a diffeomorphism if there's an inverse smooth map N to M. We know what smooth manifolds are, we know what smooth maps between them are, and we also know diffeomorphism. So let's do our first example. So in this course, we're going to keep on coming back to the two-sphere. It's my favorite manifold because you can view it as a smooth manifold in various ways, and you can view it as a complex manifold in various ways. And so if you understand just the ordinary two-sphere, something very nice to visualize. But if you understand the ordinary two-sphere, you'll really understand a lot about complex manifolds. Okay, so let's keep thinking about this two-sphere. So what is the two-sphere? It's just set of points in R3 which have norm 1. Okay, so the claim is that this topological space with the subspace topology is a smooth manifold. So I can put a smooth atlas on it. How am I going to define the smooth atlas? I'm going to have two charts. Each chart is a way of putting coordinates on the manifold, right? Getting a homeomorphism into Rm. Those x values in Rm, x1 up to xm, give you coordinates on the manifold over that chart. So here's my two charts. I've got the northern hemisphere and the southern hemisphere. Well, it's really, by the northern hemisphere, I'm being very generous. I mean everything away from the South Pole. So the entire northern part of the sphere. UN is my open set, and the identification of that with an open subset of R2 is going to be given by just stereographic projection from the North Pole. So it's going to take a point on the two-sphere and associate it to a point in the plane. Right, here's R2 here. And the point that it's going to associate to it is obtained as follows. Take a ray of light starting at the North Pole, and you shine it out until it goes through the point that you're interested in on the two-sphere. You keep shining that ray of light out until it hits the plane R2. This is where Z equals 0, right? The plane where the capital Z is equal to 0. At that point, you ask what are the x and y coordinates of that point. So it's a nice exercise to go and work out what these coordinates are in terms of my original point x, y, z on the two-sphere, and you'll work it out to be this formula. It's supposed to be a homeomorphism, so there's supposed to be an inverse map. So in fact, given any point in the plane, I can associate it a unique point on the two-sphere just by the inverse construction. And if you go and work out what the inverse construction will do, it will take a point in the plane, shine it back, and this point on the two-sphere that you'll reach back to will be given by this formula in terms of the original coordinates x, y in the plane. Okay, so that's your first exercise, just to check that. Right? If you're wanting to take the course, if you want to do exercises, then yeah, here's your first exercise. And similarly, for the South Pole, I can do stereographic projection from the South Pole. I'll get slightly different formula for how that works. Instead of 1 minus z, I've got 1 plus z. I'll open to that formula there. And here's a good exercise. What's the formula for the inverse map here? Go and work that out. And to check that this is a smooth atlas, I've got to check if the coordinate change map is going to be smooth, right? So I take a point in R2 and I project it into the I use reverse stereographic projection to the North Pole and then stereographic projection from the South Pole. And that gives me a map from R2 to itself. R2 minus the origin, because the origin is not going to be in the domain of both charts, okay, or the image of both charts. So what is that map? We've got to go and compute that map. So that's also part of the exercises. That's going to be some function of x and y, and it's a smooth map. And so that means it's going to be a smooth atlas. So yes, that's an example of a smooth manifold. I should give you an example of a smooth function on the manifold. Here's a very simple function. I just take a point on S2 and I just extract the z component. That's certainly a well-defined function. I need to check whether it's smooth. How do I check whether it's smooth? I need to look in the charts and see whether I get a smooth map from R2 to R. So for example, in the Northern Hemisphere chart, when I compute this composite here, which is I do the reverse stereographic projection and then I apply f, I think of that as a function on R2, and I call that f subscript n because it's sort of the function f expressed in the Northern Hemisphere coordinates. What will that do? Well, first of all, here's a point in R2. It will get mapped to this by inverse stereographic projection. And then I apply f. Remember what f does? It extracts out this z component, which is this divided by this. So this function here takes x comma y to this formula here. And that's a smooth map because you can see you can infinitely differentiate that with respect to x and y. So that's definitely smooth. Good. Okay. So there's a nice exercise as well. If that, yeah. The origin in R2 from the northern stereographic projection corresponds to the South Pole, and the origin in R2 from the southern stereographic projection corresponds to the North Pole, and the North Pole, those points are not in the simultaneously in the domains of each chart. Okay. Which is a good thing actually, because when you go and compute this map, you'll see that it won't be defined at the origin. Okay? So it's a good thing that I don't have to care about that. Good. So that's just our simplest example of a manifold, the two-sphere and some functions on it, but we'll keep coming back to that. So let's give a bigger class of examples of manifolds now, smooth manifolds. So given any smooth function, I want to consider the surface formed by, so I want to consider surfaces formed by algebraic equations. Or not just, doesn't have to be algebraic, just some smooth equation. So we can do this at higher levels of generality, but let's just do it at this level of generality. So consider some function from R to the m plus 1 into R. For example, the two-sphere, right? The two-sphere is given by the equation x squared plus y squared plus z squared equals 1. So that's a function from R3 into R. And then I'm asking for the inverse image where the function is equal to 1. So that would be the two-sphere. But in general, you could ask where for the inverse image of some point in R. So all the values in Rm plus 1 such that f applied to them is some constant number c. That's going to be some hypersurface in Rm plus 1. And the claim is that this is going to be naturally a smooth manifold under the condition that the gradient of f is not equal to 0 everywhere on M. Okay, we'll see that later why that's the case. But for now, just believe me. I have to tell you what a smooth atlas on this manifold will be. And here's what the atlas will be. A chart near a point X in M is going to be defined as follows. Here's my point X. Here's my surface M. I take the gradient at X, which I promised you was non-zero. I take the orthogonal plane to that gradient, which later on we'll see is the tangent space of the manifold at that point. And then other points nearby to X, I just orthogonally project them onto that plane. So this point over here gets mapped to the red point on the plane. And this point over here gets mapped to this red point on the plane. So that way I've put coordinates on the manifold M locally near X. I use the coordinates are living in this tangent plane, this red tangent plane. Okay. So that's how the smooth atlas is going to work. And also this atlas is going to have the following property. A map on this manifold into Rn, so some candidate smooth map will be smooth precisely when it is the restriction of a smooth map from an open neighborhood of my manifold in Rm into Rn. Does that make sense? So I'm wanting to know when is a map like this into some other manifold N smooth, right? So let me call it H. When is such a map H smooth? Because I'm giving you an atlas on M, and to give you an atlas, that's going to tell me when certain maps from M to N are smooth, and I'm telling you that what the property of this atlas is going to have. Such a map H will be smooth precisely when H is the restriction of some function capital H, which is defined on an open neighborhood of M. So remember, M is living inside Rm plus 1. And so I should have indicated that, so that's an error here. So this U is a subset of Rm plus 1. Okay. So that there we know what a smooth map is. So that just means a map from Rm plus 1 to R into Rn, right? Sorry. Yeah. Okay. Sorry, I should have said that this map here is getting mapped into Rn. Okay. Everyone happy with that? That's kind of a nice property of the atlas coming on a hypersurface. Good. So for example, the two-sphere is of such a form, right? So I've got a function on R3, which is just computes the squares, the sum of the squares. And I can think of the two-sphere as being the pre-image of 1, because the two-sphere is exactly the points in R3 such that x squared plus y squared plus z squared equals 1, right? And to check whether this is going to be a smooth surface, I need to calculate the gradient and check that it doesn't vanish everywhere on the two-sphere. So here's the gradient of that function. It's going to be 2x, 2y, 2z. And that's non-zero for all points on the two-sphere. Why? My screen share froze. Okay. Okay, so the question is, why is this function or this vector non-zero everywhere on the two-sphere? It's still locked. It's fine. Okay. And the answer is that, remember that to be on the two-sphere, the only place where this gradient will vanish will be equal to the 0 vector, will be where all these three numbers are 0. That can only happen at the origin. But if you're a point on the two-sphere, then you're definitely not at the origin. Okay, so that means that S2 naturally inherits the smooth atlas. And the properties of this atlas imply that if I want to determine whether a map is smooth, then all I need to do is give you a smooth function of these three variables, x, y, z. For example, this is a smooth function of those three variables. So what I'm demonstrating here is that before, to check whether a map on the two-sphere was smooth, I had to go and look in the charts. Now, these hypersurface charts are a little bit more convenient, because to check whether a map is smooth, I can give you a function of that point in R3 where the point is living, and I can just write down a manifestly smooth function, and I know that it will be a smooth map even when I go and look in the charts. Okay. So that's the definition of the charts. That was the exercise. Right. Let's give another example of a hypersurface. So, for example, the torus. The two-dimensional torus in R3. I'm giving a bunch of two-dimensional manifolds here, but two-dimensional manifolds are my favorite kind of manifolds. They're small enough to visualize, but still non-trivial. And if you want to write down the algebraic equation for the torus, a little bit of thought would sort of get you to something like this. Yeah, the radius of this inner circle is 1, and the radius of that circle is 2. So that's actually slightly dodgy. I think I've got to make this number slightly bigger than 2, but anyway. Anyhow, so to check whether something like this is a smooth manifold, you need to go and compute the gradient of this function and check that it's not equal to 0 everywhere on this torus. Okay. Good. Next section. Any questions? We find smooth maps. We find smooth manifolds, smooth maps. I've given you some examples. Okay. The next section, we're talking about tangent spaces. So, suppose I've got a smooth manifold and a point in that manifold, x. I'm going to define for you a certain vector space called the tangent space of the manifold at x. How is it defined? So I'll first define it as a set, and then I'll give you a vector space structure on that set. As a set, it's the set of equivalence classes of smooth curves from the interval from -1 up to 1, so this into M. Right? Having the property that at time 0, they're equal to x. Okay. Smooth curves, you know what that means. It means in a chart, the map is smooth, right? The two curves, gamma and sigma, are called equivalent, because I said it's the set of equivalence classes of such curves. The two curves are equivalent if in some chart around x, the derivative of gamma calculated according to the phi chart is equal to the derivative of sigma calculated according to the phi chart, right? So here's the picture. I've got my curve gamma, which is a map from interval from -1 up to 1 to M, and there's its image here in M. Okay. I've also got a curve sigma, and here's its image in M. So gamma and sigma are different, right? You can see they take on different values, so they're different. But they seem to sort of be tangent at the point x. And that means they're actually going to be equivalent. How do I know that they're equivalent? Because I take a chart around x, this phi, and in this chart, I'm going to get the composite of these curves with post-composing with phi is going to give me a curve in Rm. When I've got a curve in Rm, I can calculate its derivative just in the ordinary way. And what I want is that they'll be equivalent precisely when this derivative computed at time 0, remember at time 0, that's exactly the time at which they go through the point x. At that point here, they must have the same tangents, they must have the same derivative. Okay, so these two curves are tangent at that point, so that means that these two paths in M are equivalent. So the tangent space is a set of equivalence classes of smooth curves to that point x. Yeah. Let the hand speak. give them audio. I've unmuted it. Okay. Okay. All right. Okay. Is there a question? We'll get better at this. I'll hopefully improve my tech a little bit next week. Good. So notice, so far I've defined the tangent space as just as a set. And now I want you to notice something, which is that every chart, for example, this particular chart, gives me a bijection between the set of equivalence classes of smooth curves, so the tangent set, and Rm. Namely, you just take an equivalence class of a smooth curve and you calculate its derivative in Rm. You see, this is actually a vector here, good old vector, a column vector of numbers. So that's an element in Rm. Okay. So I've got now a bijection between the tangent set and Rm. And using that bijection, but I needed the chart to do that. And using that bijection, I can just pull over the vector space structure on Rm and pull it back into this set. That's going to equip this set now with the vector space structure. Okay. In other words, explicitly, here's how I multiply equivalence class of smooth curves by a scalar, and here's how I add two equivalence classes of smooth curves. So the thing you have to check, of course, is that this vector space structure now I'm stealing from RM using the chart phi is not going to depend on the chart phi that I'm using. So if I use a different chart, I'd get the same definition of addition and scalar multiplication. Sorry. All right. So now we've got the vector space structure on the tangent space. So let's do some examples. So suppose you've got a hypersurface of a smooth map. So that's a nice smooth manifold. Then what are the tangent spaces? For example, the two-sphere was a manifold of this form, right? You can go ahead and compute the tangent space at each point. You'll find that the tangent space as a vector space canonically identifies with a set of vectors in Rn plus 1, which are orthogonal to that gradient vector, right? That made sense. Remember the picture where I was calculating the tangent space and I said it was the vector space orthogonal to the gradient vector? Now I'm essentially stating that formally. I've given you a definition of the tangent space, and it's an exercise to go and check that according to that definition, it actually identifies with the orthogonal space to the gradient vector. Okay, which makes sense, right? If you think of the manifold, I have a point of the manifold, then here's the gradient vector to the manifold, and so it makes sense that the tangent space would be orthogonal to that. Okay. So for example, for the two-sphere, if I have a point in the two-sphere, then the gradient vector is literally just pointing radially away. So that means that the tangent space is at a point P is going to be the set of vectors in R3 which are orthogonal to P. Because here's the point P, right? I can translate its origin so that it looks like this. So the set of vectors that are orthogonal to it is going to be this space here. Okay, I'm drawing the origin of the space as if it's living at P, whereas since it's subspace of R3, I should really draw this vector space over there, but it doesn't matter where you draw it, right? And what about the torus? Well, here's the torus, and here would be an example of a tangent space at that point. So at every point, we've got a vector space. Okay. Good. So that's the tangent space at a point of a smooth manifold. So let's do a little lemma here. So suppose you've got a smooth map between manifolds. Then that's going to determine for every point in M a linear map between the tangent spaces. So the tangent space at X gets mapped linearly onto the tangent space at f of x of the target manifold. And how does that map work? Well, there's a wonderful, simple definition. I don't have to calculate derivatives or anything explicitly. I simply take an equivalence class of a smooth curve gamma that's living in here, and I just post-compose it with the map f to give me a curve in N that runs through f of x. So that's a wonderful definition of this is now what's called the derivative of the smooth map. So I've calculated the derivative without ever calculating a derivative. Do you see? Here's the derivative. It's sometimes called f lower star for short. It's the derivative of f. And it's a function from the tangent space at M to the tangent space at N. And I just take a curve in the tangent space and I post-compose it with f. Of course, in the definition of what a tangent vector is, it's an equivalence class of smooth curves, and they're equivalent if and only if their derivatives in some chart agree. So hidden deep down in the weeds, I am calculating a derivative. But the convenience of this definition is that I'd never have to worry about that. I can just think like this, and everything works out. And another point where this definition of a tangent vector as an equivalence class of smooth curves is going to be really handy is to calculate the chain rule. You know, if you want to calculate the chain rule in ordinary calculus, it's a little bit of a calculation, right? You have to do a limit and so on. Now, if I define tangent vectors as equivalence class of smooth curves, the chain rule just follows trivially. Because if I've got a map from M to N and another map from N to P, I want to compute the derivative of the composite map, right? And if you just go through this definition here, it's going to be the same as the composite of the derivatives. Okay, so let's actually prove that, just so you can see how this works. So I'm going to take the right-hand side and prove that it's equal to the left-hand side. I'm going to take this and prove that it's equal to the left-hand side. So here is the composite of the derivatives. I start with the equivalence class of smooth curves gamma. I apply the derivative of f to that, and then I apply the derivative of g to that. So first of all, I've got to calculate this. By definition, that just means it's f composed with gamma, equivalence class. Then I've got to calculate the derivative of g applied to this curve. That means I can take the equivalence class of g composed with this curve. Note where I put the parenthesis, because this thing here is now my curve. And then I do a sort of trivial thing, which is that composition of functions is associative, right? So this function here is the same as this function here. But this function here can be interpreted as the derivative of g after f applied to gamma. Okay, so the chain rule becomes a sort of triviality when you set up the tangent vector as an equivalence class of smooth curves. There's other ways to set up the definition of a tangent vector, in which case the chain rule wouldn't be so trivial. But then maybe other things would be better in those definitions. But I personally like this way of doing it. Okay, another thing that you have to think about sometimes is that, well, I gave you some examples of smooth manifolds. One major example of smooth manifold is Rm itself, Euclidean space. Okay, why? Well, I have to put an atlas on it, and I just take the identity atlas. The chart U is the entire Rm, and the homeomorphism from that to Rm is just the identity map. And if I do that, then what would be the calculation of the tangent space to that smooth manifold Rm at some point y? Well, what is the tangent space at y? It's an equivalence class of smooth curves through y. And I can, since I've got this canonical chart, which is this identity chart, I can canonically associate such a smooth curve with just a vector, right? Just the numbers, which are a column vector, if you like, which are the derivatives of this gamma at that point in the different directions. Okay. So this is important that the tangent space of Rm at any point canonically identifies with Rm. That's not the case on a general manifold. For example, this tangent space, although it's linearly isomorphic with R2, I can't write down a formula for it without first choosing a basis. There's no natural basis on this vector space. But over here, I don't need to choose a basis. I have a canonical identification. Okay. Good. Here is the promised proof of that statement I made earlier. I'm not going to go through it now, but those of you who go through the notes afterwards, this justifies the statement I made earlier, and it's justified by something called the implicit function theorem. How is the implicit function theorem proved? It's proved using analysis, namely the contraction mapping principle. Okay. Okay, we're speaking about tangent spaces. Now I want to speak about the tangent bundle. Okay. So the collection of all the tangent spaces of an m-dimensional manifold itself forms a manifold. And it's going to be a 2m-dimensional manifold. Okay. So that's called the tangent bundle. So what is this tangent bundle? The tangent bundle of an m-dimensional smooth manifold M, and we write Tm for it, as a set, it's the set of pairs x, v, where x lives in M and v lives in the tangent space at M. All right. So that's the set. I have to equip that set with the structure of a smooth manifold, so I have to define a smooth atlas on it. How am I going to do that? Well, I know M is a smooth manifold, so M has charts. So let U, phi be a chart for M. And this is going to give me a chart for Tm, because I can take Tu, that would be just a set of points where x is in U and V is in the tangent space at U. And I can identify that with the Cartesian product of phi of U, which is living in Rm, with Rm itself, by the map which sends x, v to x, the derivative of phi at V, right? Remember that phi is a map from U into Rm. So that means that at each x in U, I've got the derivative of phi, which is going to be a map from the tangent space of U at x to tangent space of Rm at phi of x. But remember, we agreed that this is the same canonically as Rm. Okay. So that's how this map works. So that gives me a chart for the tangent bundle here, for the tangent bundle, and then if you go and calculate the transition maps, they will be smooth. Okay, so here's a picture here. So I've got a one-dimensional manifold, the one sphere, S1. Yeah, Zaganya. This, yeah, Zaganya is pointing out that this area here, this is supposed to be phi of x. Yeah. Sorry, no, this x is fine. You mean this one here, huh? Thank you. That should be phi of x. Good. Okay, so let's do an example. So I want to draw a picture of the tangent bundle of S1. Okay, so here's the one sphere, just a circle. And I want to give you a chart for the tangent bundle of S1. So a point in the tangent bundle is a pair consisting of a point in S1, x, and a vector in the tangent space at x. So this red vector here is a point in the tangent bundle. Or vector here is a point in the tangent bundle. Or this vector here is a point in the tangent bundle. All possible vectors in all possible tangent spaces, points in the tangent bundle. And so how do I write down a chart for this? So what I do is I take a chart for S1, for example, here's this chart map phi. I'm going to identify this arc of the circle with just this straight line segment here. And then I'm going to take the derivative of phi and apply it to these vectors here. That's going to give me a point in R, and that's going to be the y-axis here. So this particular vector here gets mapped to this point here. If the vector was a bit longer, then it would get mapped to a bigger vector here. If the even longer, it would get mapped to a bigger vector here. But all living at over the same point 5x. Because all the points in the same tangent space get mapped to this, have the same 5x coordinates. Okay. So at least you can see here that the tangent bundle of S1, hopefully you can see, is the same thing as just S1 cross R. Okay. But that's not always going to be the case. So it's not, for example, true that the tangent bundle, so this is a canonical diffeomorphism. This is a diffeomorphism. But it's not true that the tangent bundle of S2 is equal to S2 cross R2, or at least diffeomorphic to it. Why? The point is that the tangent bundle of S1, each point in the tangent space, canonically identifies with R, with a real line. But for tangent spaces in S2, you can't identify a point in the tangent space with an element of R2 canonically, right? So here's a point in the tangent space here. Now tell me what element in R2 that corresponds to. Can't tell me unless you choose a basis, and then you're going to get into trouble. Okay, anyway. Tangent bundle is itself a smooth manifold. That's an important point. By the way, I did cheat slightly here when I was writing down the smooth atlas on the tangent bundle. I started off by giving you a smooth atlas, but to give a smooth atlas, you're supposed to first have the structure of a topological space on the manifold. Thus, a smooth manifold is defined to be a topological space equipped with a smooth atlas. And I didn't actually put a topology on the tangent bundle. So that's not such a big deal. You can always do the following. So in a way, the topology is not really important. The charts are the most important thing. So I can put a topology on the tangent bundle using the charts, right? So having knowledge of the charts, i.e. the atlas, I can define a topology on the tangent bundle by saying that a set is open if for any chart the derivative map applied to that chart is open. Right? So you can actually do this for any manifold. So you can always reconstruct the topology of the manifold from the charts. The charts that are the most important thing. Okay. Anyway, that's an exercise. If that confuses you, don't let it confuse you. Exercise it from your brains. Come back to this later. So I know I'm going through this material quite fast, but you can always watch the video later and go through the notes. Okay. So I've defined a smooth atlas on the tangent bundle, and if you go and check, you'll find that with respect to this smooth atlas, the projection map from the tangent bundle to the underlying manifold M is actually smooth, right? I've defined what this is as a smooth manifold, and I've got this projection map. What does it do? It sends a point x comma b. Remember, a point in the tangent bundle is a pair consisting of a point in M and a vector in the tangent space at that point. It sends such a vector, or so it's such a point in the tangent bundle and just projects it down to x. So that's a certain function from Tm to M, and with respect to this atlas that I've just defined, this function is going to be smooth. Okay. Good. So now that we have the tangent bundle, we can talk about vector fields on M. Because now we can say that a smooth vector field on M is going to be a smooth map from M into Tm. Which is a section of this projection map. In other words, if you first of all do the map X to get you from M into Tm, and then you come backwards via pi, then that's the identity on X. And if you write out what that means explicitly, it means that at each point X in M, I'm going to have a vector in the tangent space at X of M. That's what it means to be a section. Okay? And now I'm telling you what it means to be a smooth section, because I'm saying that that collection of vectors, when thought of as a map from M into Tm, must be a smooth map. Okay. So 99% of differential geometry, which is what we're doing here, is just setting up a language. Okay, it's just a language. That's why if you like differential geometry, you usually also like category theory, because category theory is also a language. Okay. So here's an example of a vector field on the torus. So at each point, I've got an element I've got a vector in the tangent space. So over here, it's this vector. Maybe over here, it's that vector. Over here, it's this vector, and so on. And now I know what it means to say that's a smooth vector field. It's exactly to say that when thought of as a map from M to Tm, then that's a smooth map. Okay, so where are we? We're doing good. I think we should take a 10-minute break, and so we can mute ourselves and have a little break, and we'll be back just after 3. Dario has raised his hand.
Hi, Bruce. Sorry, I'd like to ruin your break. I just wanted to ask, so obviously a bunch of our definitions that we've made here depend on a particular representative of our equivalence class of atlases that we've chosen. So we're skipping over some details here because, like, we know what it means for 2 different atlases to say that the same function from M into R is smooth, for instance, but we don't know what it means for 2 different atlases to say that the same function from M into N is smooth, for instance. So when we define a smooth map between 2 manifolds, one of them not R, it seems a priori like that's dependent on our choice of atlas, at least our choice of representative. Yes.
No, quite right. Quite right. So, but then, yeah, that would be a lemma that would say that the smooth atlas gives you, tells you which functions from M into R are smooth, but it also tells you which functions from M into any other manifold N are smooth, or any other set equipped with a smooth atlas are smooth. And it would be, to know whether the functions are smooth is equivalent to knowing whether these maps are smooth, actually. So,
right, and similarly in the other definitions, like the definition of the tangent space, where we talk about 2 curves being equivalent if in some charts they are, tangential. Like again, that
no, that's quite right. That's quite right. And actually, thinking along those lines leads you to important places. So, for example, if you want to talk about smooth manifolds which are infinite dimensional, how would you define that? So there's various ways you could do it. You could just try and do the same definition you've just been doing, and you'd have a sort of homeomorphism with an open subset of R infinity. But what exactly do we mean by R infinity? We have to put a topology on that, and so you can do it that way, and you can talk about Fréchet, smooth manifolds, and so on. But you could also think along the sort of more synthetic routes, which is to say that a smooth manifold is a gizmo which tells you when a curve inside it is smooth. So it's like a right. set equipped with an oracle which tells you which curves inside it are smooth.
Right, that's like a more intrinsic.
Yes, and you could also do it the other way around. You could say a smooth manifold is an oracle which tells you which functions on it, outside or away from it, are smooth. And these 2 things are not exactly the same, and so there's some complications there, but that is a very useful way of setting up infinite dimensional smooth manifolds. Yeah.
If I wanted to read about infinite dimensional smooth manifolds, do you have a reference for me?
Yes, it's I'll put it on the websites. Yeah.
All right, sweet, thank you.
Okay.
I suppose this also leads one to defining the smooth atlas as a maximal atlas as opposed to an equivalence class of atlases. So you don't have to ever worry about these equivalence classes.
Good point. Good point. That then I would avoid this. That's true. Good point.
Anyway, I'll see you in a minute.
Thanks, Dr.
Thanks.
Audrey, check if you can hear my volume. I'm going to try and get it back on my iPad. I was going to run into trouble with my battery. Phone. How's the volume now? Is this fine? Okay. Okay, cool. But I think I'm going to run into trouble here again. Is it? How about the audio now? It's gone soft again. Sounds fine. And now I'm going to change to this. How's that? Did it change in any way? I'm just talking voice isolation versus wide spectrum. So now I'm trying voice isolation. I wonder if this sounds a little bit different. Pretty much the same. And then wide spectrum, is that sounding similar? Pretty much the same. Okay. Okay.
Thanks. Sorry about this, and now you've got a crowd around there. Oh no. It works, but
Yeah, I'm not sure. I don't think I've ever seen someone use a projector before.
yeah.
Well, that needs to be like a dongle.
Like this thing does sometimes have problems. Some of the university things don't accept it, so it might be that. It might just be that this thing's just not seeing the source, because usually I would at least see, I would pick up that it was picking it up, but I just wouldn't see any signal.
You know if this is the same projector that was in here before?
It's a new one.
Because I think before there was one pointing that way.
That's right. Then we got new projectors. Okay, so let's start again. I'm hoping that everyone can hear me. So just stop. Thank you. I got some thumbs up. Okay. Great. So we're going at a good speed. That's good. So I want to do another example. So, I want to do an example of a vector field on a manifold. Okay, smooth vector field. So this is more. This is a really important example. So take a chart of the manifold, right? And that means I'm going to write it. So it's some homeomorphism from U into some open set of Rm, and I'm going to write it like this: a point P in the manifold, or point P in this open set, is going to get mapped to what I'll call x1 up to xm. Otherwise, I would have to write phi of P subscript 1, comma, phi of P subscript 2, and it just get notation heavy. So I'm just calling those x1, comma, dot, 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 xm. Okay. And then, so for each P now in this chart, we're going to get the coordinate tangent vectors, which I'll write like this: del but del x1 at P, comma, dot, 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 comma, del but del xm at P. So these are certain tangent vectors living inside the tangent space coming from a chart. And how are they defined? Well, remember, tangent vector is an equivalence class of smooth curves, so I have to tell you what smooth curve it is. And it's just the curve I don't know why I've got a D naught here. That doesn't seem important. But for example, the DI is the curve in which I take the chart. So I look at RM, and I've got these canonical coordinate curves where I just change the ith coordinate. So for example, here's a curve that goes through the first coordinate. So the first coordinate is equal to t, and the rest is equal to 0. And here's a curve which goes through the second coordinate. The second coordinate is equal to t, and the rest is equal to 0. And I just map these back into the tangent space. So I use these curves, and then I transfer using the inverse chart map to give me a curve, to give me curves in M, and then those curves are going to be these coordinate tangent vectors. So it can alternatively be thought of in, so let me write it in two ways. I can think of it either as phi inverse applied to these particular curves. So there's, let me call it gamma I. Gamma I is the curve, let me call it maybe in Rm, which at time t looks like this, right? And its derivative at 0, right? Well, it's just going to be the vector which is 0 everywhere except in the ith component where it's 1. Okay, and that's what we write as EI, normally the ith standard basis vector of Rm. So I can think of these coordinate vectors in two ways. I can either think of it as being the equivalence class of the curve, of this particular curve in M, but by definition, that's the same thing as taking the derivative of the inverse chart map and applying it to these standard vectors in Rm. Okay, so it's just, that's why I wrote it down the way I did. So the claim is firstly that at each point P, these coordinate tangent vectors form a basis for the tangent space. And then secondly, that each of them is actually a smooth vector field on that chart. Okay, and I think I should make that an exercise, which I will do. And moreover, in fact, using these coordinate vector fields, you can check whether any vector field is smooth. Namely, a vector field x on M is smooth if and only if, when we expand it relative to the coordinate vector field basis coming from a coordinate chart, right? Because I've told you that these guys form a basis for the tangent space at every point P. So over here, it's this basis. But when I move the tangent space over here, then I'll get, they might be pointing slightly different directions now. But at every point, I've got a basis for the tangent space as long as I'm living in that chart. And so since I've got a basis for the tangent space, it means that any vector in the tangent space can be expanded in terms of these basis vectors. And that's going to give me a bunch of functions, x1 up to xm. And if I run through the definition of what a smooth vector field is, it's equivalent to saying that these functions here must be smooth, the component functions. Good. So in the end, the way that we work in differential geometry is we phrase everything globally in terms of tangent spaces and bundles, and we try and avoid using coordinates when we're setting things up in the language. But when we have to go ahead and do a calculation, then we go and work in a local chart. But we try and avoid working in the chart because it does make things look complicated. You've got a bunch of symbols and superscripts and subscripts. Some people love working with that. That's more an index or tensor notation for doing differential geometry. I prefer to keep things as abstract as possible, but at some point you do have to roll up your sleeves and do a calculation, do some calculus, right? Actually differentiate something. All right. So for example, let's do one of those calculations right now. And I mean, I love doing them. It's not that I have a beef with them, but we try and postpone them till the last moment. Okay. So here's the example. So express the latitude and longitude vector fields, del theta, del phi. Remember I said that for any chart, you get these coordinate vector fields according to that chart. So I've always got the latitude and longitude coordinates on S2. So that's going to give me these coordinate vector fields on S2. And I want you to express these vector fields relative to the basis coming from the stereographic projection vector fields. The stereographic projection is a different chart on S2. So it's going to have its own coordinate vector fields. Right, so let's understand what's going on here. Here's the two-sphere. Here's a tangent space of the two-sphere at a certain point. And there's two charts on this two-sphere. Well, there's lots of charts, but I'm singling out two. One of them is going to be the latitude and longitude chart. We haven't really spoken about that up to now, but that's an important chart on the two-sphere, right? It assigns coordinates to the point theta and phi, namely where theta is the angle from the z-axis and phi is the angle from the projection of that point onto the xy plane, the usual theta phi coordinates on the sphere, right? That'll be a chart. defined everywhere except at the south and north poles, then you'll have to get other charts there. But it's definitely defined over here. And so that gives me a certain chart. I've also got a different chart, which is the stereographic projection from the North Pole. That's going to get me into coordinates, which I'll call X and Y. All right. And each of these charts comes attached with its own coordinate basis for the tangent space. So, for example, for the theta phi vector fields, del theta will be the curve which points in the direction of increasing theta. So if you're at this point and you increase your theta, in other words, you're increasing your latitude, then you're going to be moving along this curve here, right? So the tangent vector is going to be pointing down. If you're at this point and you're increasing your longitude, so you're increasing phi, then you're going to be moving around the curve. That's going to be del phi. Alternatively, if I think in terms of stereographic projection, if you're at this point and I'm increasing the x from the stereographic projection, then I think you'll agree that I will be moving up the sphere. So I think I've got these the wrong way around here. And if I increase, I think I just meant to say EX and EY there. And if I move in this direction, then I'll be moving like this on the sphere. So there's two different bases for the tangent space. I'm wanting you to express the green basis vectors in terms of the black basis vectors. So let's do a little calculation. So what do I need to do? I can do this calculation over here, or over here, or over here. I'm going to get out the same numbers. I'm choosing to do it over here. So what I've got the equivalent picture over here. I've got the black basis vectors, which is obtained by taking them over here, which is the standard basis vectors, and then just transporting them over by the derivative of this map. And then I've got the green basis vectors, which are the standard basis vectors here. So I'm asking to express the green basis vectors in terms of the black basis vectors. So how do we do this? So first of all, let's just understand how theta and phi work. Remember, I can express x, y, and z in terms of theta and phi like this. And that means if I want to write down my stereographic projection coordinates, small x comma small y, in terms of theta and phi, remember small x comma small y is given by this formula in terms of capital X, capital Y, and capital Z. On the other hand, capital X, capital Y, and capital Z are given by this in terms of theta and phi. So yeah, I've written down this explicit coordinate change map from theta phi into xy. It's this formula here. Okay. So then I'm not going to go through this calculation, but you can just go ahead and calculate it. It's important for you to work through this. And then here's my calculation. I calculated that del theta is equal to this number times del x plus this number times del y. Okay, now I'm just doing multivariable calculus here, right? And I actually do this calculation in two ways. The first way is sort of by first principles, thinking in terms of equivalence classes of curves. But in the second way of doing it, which I do want to demonstrate for you, I reason as follows, right? So for example, someone asked me to compute del phi as something times del x plus something times del y. How do I compute these numbers? Here's what I do. I think of how this del phi operates on a smooth function. And then I just sort of use the mantra of the chain rule for multivariable functions, right? If I want to differentiate f with respect to phi, it would be the same as differentiating f with respect to x times the derivative of x with respect to phi. Plus the derivative of f with respect to y times the derivative of y with respect to phi. So we're all happy with this line. And now all I've done is I've just rearranged it by taking these terms and putting them in front. Right? So that gets me here. Everybody happy with that? Right? This del x now means the operator which is going to differentiate f with respect to x. It's just shorthand for, so when I write down something like this, I mean the derivative with respect to x. Okay? So from this calculation, we can see explicitly that this thing here must be equal to this thing here. You see how that works? Okay, so that tells me that to calculate del phi, I must calculate the partial derivative of x with respect to phi. That'll be the component multiplying del x. And the component multiplying del y will be partial derivative of y with respect to phi. So then I can just calculate that there. Good. Okay, any questions about this calculation? It's a nice little calculation of the kind that you need to be able to do. Good. And just to close with this, by the way, for example, yeah, I can check that these guys are smooth vector fields because these functions, yeah, these component functions are smooth, right? Okay, on their domain. So, for example, you do run into trouble when this denominator will be 0, but that's not going to be on the domain of the chart. So, away from that, it's going to be perfectly smooth. So, just to mention here, the so-called hairy ball theorem, what does that say? This is now stated in terms of smooth vector fields. It tells us that there's no smooth, nowhere vanishing vector field on the two-sphere. So here's the two-sphere, and I try and construct a vector field, a smooth vector field on the two-sphere. Here is one example. You can think of putting a vector field on the two-sphere as sort of combing the hair on the sphere, right? And yeah, I try to sort of comb the vectors downwards. But at any way I try and do it, for example, this way, I'm going to run into trouble at some points. In this particular construction, I'm running into trouble at the north and the south poles. It's like I've got a crown in terms of the hair. And the theorem is saying that, in fact, that'll always be the case, that because of the topology of the two-sphere, there's no way that you can construct a smooth vector field on it which is nowhere non-vanishing. This thing is a smooth vector field, but I had to then make these vectors get smaller and smaller as they approach the north and south pole till there was 0 over here. But I couldn't define them over here because in which direction would they, I couldn't make them non-zero here because in which direction would they point? If they pointed this way, then there'd be a discontinuity there, right? Okay. So that's true actually for any even dimensional sphere. Conversely, every odd dimensional sphere does admit a nowhere vanishing smooth vector field. Okay.
I also asked that there were two methods for calculating things that you want to RP equivalent. Because I think you probably have to do some trig simplification there or something.
Okay, so what I did was I used method 1 to calculate del theta, and then I used method 2 to calculate del phi.
Right, okay, yeah, see now, I'm sorry.
That's good. No, that's fine. I sort of minimized my space requirements. Okay, good. Next section, vector bundles. Okay, so we've learned about smooth manifolds. We've learned about tangent spaces. We've learned about the tangent bundle of a manifold. Now we're going to generalize that concept of the tangent bundle to vector bundles. So, the tangent bundle of a smooth manifold is not just any old smooth manifold, right? Remember, if M is an m-dimensional manifold, the tangent bundle is a 2m-dimensional manifold. But it's not just any old manifold. It comes equipped with a projection map from Tm into M, right? Which takes pair x comma v and maps it down to its base point x. And that's just not any old map either. That map has the property that the fibers of that map for any point x have a vector space structure. Okay, so this is a manifold. I wouldn't expect the fiber of a map between manifolds to have a vector space structure, but this particular one does. So I think of it as a bundle of vector spaces, because at each point x, I've got a vector space. So it's like I've got a bundle of vector spaces. Okay. So let's axiomatize that kind of structure. So a smooth real vector bundle of rank k over a manifold M is a collection of k-dimensional real vector spaces parameterized by the points in the base manifold. Okay, that's what it is first and foremost, satisfying some properties. But it's a collection of vector spaces parameterized, k-dimensional vector spaces parameterized by the base manifold. What is the extra properties that that collection of vector spaces must have? It must come equipped with a smooth atlas on the total space. The total space E is the disjoint union over all the points in the base of these vector spaces EX. So that's just a set, and on that set you have to put a smooth atlas. Well, this not just and that smooth atlas is not any old smooth atlas. That smooth atlas must have the property that the projection map must be smooth, and one more property, that the base manifold M can be covered by open sets U, where each U is equipped with a diffeomorphism between the vector bundle restricted to U and U cross RK. It's a k-dimensional, so rank K vector bundle, so I should say K there. And that diffeomorphism is not just any old diffeomorphism. That diffeomorphism commutes with the projection maps onto U and restricts to a linear isomorphism of vector spaces on each fiber. Okay, so it's mouthful to take in, but let's draw a picture. Okay, so what's going on here? A vector bundle of rank K is first and foremost a collection of vector spaces, k-dimensional vector spaces, parameterized by the points in M. So on the left here, I've got M, and then I've got a collection of vector spaces. At each point, I've got a vector space, a k-dimensional vector space at each point in M. Okay? I've drawn them as lines here, but these are k-dimensional vector spaces. Good. But when those k-dimensional vector spaces can be put into a big total space, I can take their disjoint union, right? And I call that the total space of the vector bundle. And that disjoint union, that must come equipped with the structure of a smooth manifold in such a way that if I project onto the base space, that's a smooth map. And also, it must have the following property, that the base manifold M can be covered with charts U, where on each U, I can restrict this vector bundle to the points in U, right? So I'm just talking about the vector spaces which are parameterized by the points in U. That's what I call E restricted to U. And what I want is that associated to this open set U, I have a diffeomorphism from the collection of all these vector spaces, so the total space restricted to U, to U cross Rm. You see, Rm is just a trivial, sorry, I should say Rk, the k-dimensional vector space. And moreover, that this diffeomorphism respects the fiber structure. In other words, if a point above y gets mapped to a point above phi of y, then another point above y should also get mapped to the same another point above phi of y, right? So it restricts to a fiber by fiber map. And moreover, at the level of the fibers, that map must be a linear isomorphism, because this is a vector space of rank up. This is a k-dimensional. That red line is a k-dimensional vector space. And similarly, this red line here is a k-dimensional vector space. It's just Rk. And then what I'm wanting is that this psi restricted to each fiber is actually a linear isomorphism of vector spaces. Okay. So it's something to take in, but what's a nice example? The nicest example is just the tangent bundle of a manifold, right? Because at each point, I've got this vector space, and that assembles to give me a smooth manifold, and it satisfies the axioms. Why does it satisfy this last axiom? This is called the local triviality axiom. Because if you think about the charts on the tangent bundle, they were constructed exactly in this way. Okay. this axiom is saying that the bundle is locally trivial because this thing here is a trivial vector bundle. Whenever you just have a product bundle, that's called a trivial vector bundle. So we're not saying that globally the vector bundle E is equal to M cross RK, but we are saying that locally it's equal to U cross RK. Okay, so just like if you think about the tangent bundle of the two sphere, I said to you earlier, so here's S2. I said to you earlier that the tangent bundle of the two sphere is not the same as the two sphere times R2. It's not diffeomorphic to that. But locally it is true. So if I take a chart, for example, the stereographic projection charts, then I can say that the tangent bundle of the two sphere restricted to that chart is diffeomorphic to just U cross R2. Okay, so it is locally a product, but it's not globally a product. How do I know that the tangent bundle is not globally a product? So how do I know that this is not true? Well, if it was globally a product, then I would be able to define a smooth, nowhere vanishing vector field on it everywhere. Because if I've got a product bundle, I can just take the sort of the E1 vector in R2 and just put that everywhere. But I discovered that on the tangent bundle of S2 by the Hairy-Ball theorem that was not possible. So there's no way that the tangent bundle of S2 is a trivial bundle globally, but it is locally a trivial bundle. Okay. Obviously, another important example is just the trivial bundle. So for any manifold M, you can always take the product of M with RK, and that will be a vector bundle of rank K. It's called the trivial vector bundle of rank K. Another example I just want to mention quickly is the normal bundle of a hypersurface in Rm plus 1. That's going to be a bundle of rank 1. So here's an example. So I've got some M living inside one dimension higher Euclidean space. So for example, the two sphere living inside R3. At each point of the two sphere, I can take the vector space orthogonal to the tangent space at that point. So I've got the tangent space at that point. And then I can take the vector space which is orthogonal to the tangent space, which we know is basically the same thing as the vector space spanned by the gradient vector. That's going to be a one-dimensional line because a hypersurface is living in Rm plus 1. So there's already m dimensions over here in the tangent space, so there's only one dimension left over for the normal bundle. Okay, but anyway, that's a one-dimensional vector bundle over the surface M. And in fact, the manifold is called, or the hypersurface is orientable, which we will define later, if and only if this normal bundle is trivial. Okay. Okay, good. We now know what a vector bundle is. Any questions on that? So I'm going quite fast, but you can review the notes afterwards. Good. Now we're going to put our algebra hats on and do some algebra because we have to prepare to speak about differential forms. And to speak about differential forms, we need to know about tensor products and duals of vector spaces and so on. So there is all this material that I'm about to talk about is covered in the reference by Luyenga in the appendix. So you need to work through this by yourself. Okay, it's just some basic linear algebra which you might not have covered in your undergraduate. I didn't when I was doing undergraduate. It's not normally covered, but it is something that you need to know at postgraduate level, the constructions that I'm talking about here. So we're not talking about manifolds anymore. We will apply this to manifolds in a second, but for now, we're just talking about linear algebra, actually what's called multilinear algebra.
Okay. So there's a bunch of constructions that you can do when you have a vector space. So I give you a vector space, any vector space. You can form its dual space. By definition, the dual space, written V superscript star, is by definition vector space maps from the vector space into the ground field. For me, the ground field is just the real numbers here. Okay. If you've got if E1 up to En is a basis for V, so there's E subscript I, then E superscript I defined as follows, right? To define a linear function from V into R, just have to define it on a basis. And these guys, when you feed them the E subscript J's, they give you out delta Rj, right? In other words, for example, E1 acting on E superscript 1 acting on E subscript 1 is 0. But E superscript 1 acting on E2 is, this is going to be 1, this is going to be 0, and so on for all the rest. And so on for the other guys, right? So that's the construction of the dual space of the vector space. Doesn't have to be a finite dimensional vector space. You can still construct the dual space, but if the vector space is finite dimensional, then the dual space has the same dimension as the original vector space. And if you choose a basis for the original vector space, then you get this corresponding dual basis for the dual vector space. Good. It's a good exercise to work through this and to prove these things just from the axioms of a vector space. Right? Another construction that you can do with vector spaces is that for any set X, you can construct the vector space of formal linear combinations of elements in X. So for me, my ground field is the real numbers. So R bracket X is a set of all formal linear combinations like this. So it's some real number times the formal vector corresponding to X1 plus dot 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 plus some real number times the formal vector corresponding to Xn. So these X1 up to Xn are elements of X, and these A1 up to Ans are scalars living in R, and N is some natural number. So, okay, happy with that? So for example, if X has 5 elements in it, then R of X will have dimension 5. If X has infinitely many elements, then R of X will have infinite dimension. Okay. The addition and operation here is just formal addition, right? Okay. So we're going to need that construction now because we have to talk about tensor products. So if I've got two vector spaces V and W, I can form their tensor product. How do I define that? Well, I take the Cartesian product as a set, and I take the vector space spanned by that set in the sense I've just described up here. So this is some massive infinite dimensional vector space because V is a set containing infinitely many elements, right? So I take this massive infinite dimensional vector space and then I quotient it by a massive infinite dimensional subspace. What is the subspace I? It's the subspace spanned by vectors of the following form. I take the formal vector corresponding to V1 plus V2, comma W. So I've got some vectors V1, V2 in V and W in W. And I've got this formal vector here living inside that space, right? It's one of the basis vectors for that space. And then I can have this formal vector and I've got this formal vector. And since I'm living in this space here, I can take formal linear combinations of these vectors, right? And I consider this, and similarly, this one here, and this one here. I can consider the subspace spanned by these vectors. So that's again some massive infinite dimensional subspace of this massive infinite dimensional space. And I take the quotient of those two, and that's the tensor product of V with W. It has a certain universal property which is important, but I don't need that right now, so you should look this up. But I wonder how many of you have seen the concept of the tensor product of vectors spaces. Brian, you've seen it. Audrey? In physics terms, that's good enough. That's fine. Okay. Online, who's seen the, or who hasn't seen the tensor product of vector spaces defined like this? Okay. Good. So I write the equivalence class of a vector now in this quotient space as V tensor W, right? Just in terms of notation. So this is all just a complicated way of saying things like this. I want to be able to say, for example, that V tensor 7W is equal to 7V tensor W, right? I want to say, for example, that V1 plus V2 tensored with W is equal to V1 tensor W plus V2 tensor W, okay? These statements are not true in here, but they are true in the quotient. Okay, because I precisely made sure that they're true in the quotient by quotienting out. See, for example, to make sure that this is true, this comes from this guy here. Sorry, this guy here. I know that these two guys differ by an element of this form, and this form, an element of this form is 0 in the quotient. Okay, so it takes a little while to think that through, but that's what the definition abstractly of the tensor product of vector spaces is. And this is a nice definition. It's a basis-free definition, and it works for any pair of vector spaces. So one thing to bear in mind is that not every vector in the tensor product of two vector spaces is of the form V tensor W. Okay, it's not like, this is something to understand about tensor product spaces. It's not like the Cartesian product of the vector spaces, right? You know that the Cartesian product of vector spaces is also thought of as known as the direct sum of vector spaces. There, the elements are just pairs, V comma W. So every element in the Cartesian product is just of the form V comma W. But every element in the tensor product is not of the form V tensor W. There's more elements in there because you can take linear combinations of such elements. So for example, take a two-dimensional vector space spanned by E1 and E2. Now, this vector here, E1 tensor E2 plus E2 tensor E1, that's going to be an element in V tensor V. But you can't write that element as some vector in V tensor some vector in V. Try, and you'll fail. All right. This is the source in quantum mechanics of entanglement, right? Because the wave function is sort of this form, and that means that you can't separate it as a product of two systems. Anyway, the tensor products are really important in quantum mechanics. So how do I get a basis for the tensor product space? So suppose V is finite dimensional, and I've got a basis E1 up to EM for V, and suppose F1 up to Fn is a basis for W, then these product vectors, EI tensor Fj, will be a basis for the tensor product space. I'm not saying that every vector in the tensor product space is a product vector, but I'm definitely saying that every vector in the tensor product space is a linear combination of product vectors, namely, for example, these ones. Okay. Good. So we've done some linear algebra. We've talked about the dual vector space, and we've talked about tensor products of vector space. We're going to need another notion, which is the exterior product of vector spaces. And to talk about that, I first of all have to talk about the tensor algebra, right? So I know what the tensor product of two vector spaces is, but I can take the tensor product of k vector spaces. So by that, I just mean V tensor B, and so on, k times. And I could, if I want to, I could sum them all up. So I could take the tensor product of no vector spaces, so V tensor with itself 0 times, that's just the ground field by definition.
Then I could take V tensor with itself once. So V tensor with itself once is just V. And then I could take V tensor V, V tensor V, tensor V, tensor V. So I could form this big vector space. Why am I doing that? Well, because this big vector space, which I'll call T of V, is actually an algebra. It's not just a vector space. Because if I've got, I can define a multiplication operation on this vector space here called the tensor algebra. I just need to define a multiplication operation, take two homogeneous elements. So here is, for example, a typical element in V tensor V, and here's an element in V tensor V tensor V. And to multiply them, I just concatenate them. Okay, so that's defining multiplication on tensor elements or product elements, and then I define that multiplication, extend it out to the whole vector space by linearity. Good. So now, from any vector space V, I can canonically form an algebra, tensor algebra of V. It's a big infinite dimensional vector space. Even if your original vector space was finite dimensional, the tensor algebra is infinite dimensional, but it's still sort of trivial, right? Now, given the tensor algebra, I can form the exterior algebra. How do I do that? It's again a quotient space. The exterior algebra is a new algebra where I take the tensor algebra and I quotient it by an ideal, which is again a subspace, and it's the subspace spanned by vectors of this form. So it's called a stammering tensor. So you take a product of vectors, a tensor product of vectors, where two successive vectors in the tensor product are equal. So maybe V1 is equal to V2, or maybe V2 is equal to V3. So the subspace spanned by stammering tensors, that's going to be a certain subspace of the tensor algebra. Why? And it's an ideal because if you multiply them together, they stay like that. And if you multiply with them with something in the tensor algebra, you still get a stammering tensor. So it's an ideal in the tensor algebra. So I can form this quotient algebra. And that quotient algebra is called the exterior algebra. Okay, so I've done a bunch of abstract stuff, but it's all undergraduate level. It's not maybe stuff you haven't seen, but it is stuff just using undergraduate level maths, right? I've needed the concept of algebra, I needed the concept of a vector space, and that's all I needed. Okay, so just to be clear, the exterior algebra then splits as a direct sum. There's the zero part, which is going to be where I take the zeroth part of the tensor algebra and I quotient by I. Then there's the parts of degree 1, parts of degree 2, parts of degree 3. And as I said, by definition, exterior algebra at level 0 is just the ground field. At level 1 is just the vector space B, and I can carry on. Taria's got a question.
Yeah, sorry, I'm failing to see how the oh goodness, the echo. I'm failing to see how the product of a stammering tensor with an arbitrary tensor remains in the following tensor. For example, if you take one of those stammering tensors and you multiply it with like a sum of two tensors, like 1 plus v or something.
Okay, let's do that. So I take 1 plus b, and I multiply it with, say, w tensor w, tensor d. Okay. So what am I going to get out? By definition, I'm just going to extend this multiplication linearly, so I'll get this. So you see, this is in the ideal I because it is a linear combination of stammering tensors. That's a stammering tensor, and this is a stammering tensor because of that part there. I think I crushed Dario with my my response, but I think it's more likely that he muted himself. Okay. Okay. So, just to give a notation, the equivalence class of this tensor in the tensor algebra, or the kth homogeneous part of the tensor algebra, is written using wedge symbols. Okay, so this is all very abstract, but at least I've given you definitions that are basis free. And now, more down to earth level, you can think of these wedge product as just being an anti-symmetric way to combine vectors together. So in other words, V1 wedge V2 must equal minus V2 wedge V1, because they will differ by a stammering tensor. Because you see, let's do that little calculation. Why? Let's check this. Well, what do I know? I know that V1 plus V2 wedge V1 plus V2 is equal to 0 because it's a stammering tensor. Right? So if I multiply this out, this is saying that V1 wedge V1 plus V1 wedge V2 plus V2 wedge V1 plus V2 wedge V2 is equal to 0. And this guy is also equal to 0. And this guy is equal to 0 because they're stammering tensors. So then that means that V1 wedge V2 must equal minus V2 wedge V1. Okay. So all of this is just a complicated way of saying that I want to be able to put vectors together in an antisymmetric way. So in summary, if I've got a basis for V, E1 up to EM, then how do I get a basis for the kth exterior algebra of a vector space? Well, what I do is I need to put these vectors, I need to multiply them together from left to right in a way that I don't want to overcount them. So I need to take into account that E1 wedge E2 is minus E2 wedge E1. So I can't include both E1 wedge E2 and E2 wedge E1 in the same basis. So what I'll do is I will order them. So I'll take wedge products like this, where this index here is less than or equal to this index, or less than this index, less than this index, and less than this index, right? And that ensures that I'm never going to overcount in my basis. Okay. Good. So there's some exercises there for you, but those are exercises that you can do, but we don't have to talk through them now. So I have completed the lecture. Are there any questions? You have survived. Congratulations. You're now at a crash course in smooth manifolds. Next week, we will speak about differential forms on smooth manifolds, and then we'll start with complex manifolds. Okay, so Audrey has asked, is there some intuition for this wedge? Very good question. Yes, because I want to think of it. I want to think of a V wedge W as an oriented area element. Exactly. So if you've got V and W, then this sort of thing here, the area between them, that is how I want to think of V wedge W. And it's an oriented area in that if I were to write down W first and then V, I would get the minus of this. And then if you have three vectors, then you get a cube. So the exterior algebra is a brilliant way to talk about little volume elements inside your vector space, oriented volume elements. Okay. And that's why, and we need them if we wanted to do integration on the manifold. So the integration would be adding up a bunch of volume elements or a bunch of area elements. So then I would need to use wedges. Yeah. It's a one subtlety here is that it's when I speak about an area of something, that's a number. So to actually calculate the area, I would have to then have a function on the set of area elements. The area elements themselves are these geometrical things. But the area of an area element would be then a function on the set of area elements. So that would be the area would be a function in an element of the dual vector space. Right? So in other words, lambda 2 of B is the set of sort of area elements in B, oriented area elements. And if I talk about the dual vector space of that, that would be the set of all possible areas that you can define on B, so area functionals. Okay. Okay, thanks for listening, guys, and I'll update the notes and put the references down, and see you next week.